Hello, today we are going to solve the quantum harmonic oscillator in one dimension. So we're going to consider the one-dimensional time-independent Schroedinger equation. It's cut squared divided by 2m, and here we have our potential energy times phi equals to W. This is the energy parameter times phi, and the potential energy in a harmonic oscillator is by definition a quadratic term, and the constant term is often written like this because it has a direct physical interpretation, with this being the mass of the particle and this one being the frequency of the oscillations squared. And now we are going to multiply everything by this term, so we will get d squared on dx squared minus small u phi equals k squared phi, where obviously small u will have to be 2m divided by h cut squared times u, and k squared is the same but with w, so it is 2m divided by h cut squared times w. So we are now going to take everything to the left side, and we get plus k squared minus u squared phi equals 0. And now we are going to consider a dimensionless quantity instead of x. So we are going to write we're going to consider c equals x divided by L, and so we are going to get 1 divided by s squared times u squared phi divided by g k squared or c squared, and plus, now we're really going to multiply everything by s squared, so we get s squared k squared minus this times s squared, and we're going to use the potential energy. We're going to plug in the potential energy, so small u is this one times this factor, and it becomes m squared omega squared divided by h cut squared times x squared, and we are multiplying by s squared, so we're going to get s squared, and instead of x we are using this one, so we're going to get s squared x squared, so s squared here becomes l to the 4th, and here we have this term here. Now L is chosen in such a way that this becomes 1, so that here we have c squared, here we will get simply minus c squared, so it's chosen in such a way that L to the 4th is equal to h cut squared divided by m squared omega squared, which means equals to h cut divided by m omega to the 1/2, so it is the square root of this thing here. This is our final equation, but now we are going to do another substitution. Now the meaning of these substitutions will be clear soon. We're going to substitute s squared times k squared by 2n plus 1. So we're not considering k now, we're considering n, and we will get d squared phi, I write it directly here, 2n plus 1. So now we are considering this form of our equation. Now all this was mathematics. Now it comes the physical consideration. Not all the solutions to this equation, in fact, we have a physical meaning. Most of the solutions to this equation are not interesting because they make no sense physically. In fact, for the wave function to have a physical meaning, it must be normalizable, and in particular it must go to 0 at the infinity, because otherwise it is not normalizable. So we can't have, for example, an exponential form of the wave function like this, because it goes to infinity, we can have with a minus sign, for example. So to find these solutions which make sense, we consider this equation at the infinity. So we study the solution at the infinity, and at the infinity this term is negligible, because this term is much larger, and we get minus c squared phi equals 0. And this equation here has two independent solutions of the form plus or minus k squared plus or minus c squared divided by 2, and the plus solution makes no sense because it would grow, because the wave function would grow at infinity when x tends to the infinity. So we're going to take only the solution with the minus sign. And to get a general solution to our starting equation, we make this ansatz. So we make this guess, which is that the solution to this equation is a function, a generic function of c times the solution at the infinity. So we have simply written a very general form, taking out explicitly the solution at the infinity. So we're now going to substitute here, and to substitute here we're going to calculate the derivatives. So phi prime of x is h prime minus c h times the exponential, this exponential here, and the second derivative is h second minus h minus c h prime, plus, now we're going to multiply this by minus c, so we're going to get minus 2c h prime plus h squared, sorry, c squared h times the exponential. So we're now going to substitute here, and when we substitute here, this term here cancels out with this one, because here we can write phi as h times the exponential, and this term here cancels out with this one. So we are left only with h second minus 2 psi h prime plus 2n h times the exponential equals 0. We divide everything by the exponential and we get this equation here. So this equation here is a well-known and studied equation. It is called the Harmonic equation. Now, the solutions to this equation will depend on the parameter n, and for most of the values of n, they will diverge as x tends to the infinity. And to get the convergent solutions, we must have n to be an integer. Only if n is an integer, we can get convergent solutions. So our spectrum of solutions will be discrete, and this is mathematically where the discrete solutions of quantum mechanics, in the case of the harmonic oscillator, come from. So when we have n a natural number, we will have this function have two dependent solutions. One diverges, the other one, which would usually be of this form, and this form diverges, because if h is equals to this, then you multiply by it, you get h squared divided by 2, which diverges. Where this form here, this solution here, when n is integer, becomes a polynomial. So we have a degeneracy of this solution B here for integer n, and this degeneracy allows us to have convergent solutions, right? Because if h is a polynomial, and a polynomial times this will converge, because as c goes to the infinity, no matter how big the power of the polynomial will be, this will always grow slower than the decay of this term here. So the only solutions which make sense are the polynomial solution for h, and these polynomials are called the Hermite polynomials. So our general solution will be a Hermite polynomial times the solution at infinity. Now we will have a Hermite polynomial for each value of the parameter n, and Hn is called the Hermite polynomial of degree n. Now the way these polynomials are written could differ by a constant, and they are not necessarily written found in tables with the conventions for which we have a normalized phi, so they're not usually written in a form which is already normalized for our problem, so we will need anyway to add a constant n of normalization, and the form they're usually written is minus 1 to the n times u to the xi squared, the nth derivative of e minus xi squared. Now the Hermite polynomials have this property that when you multiply each one by this term, they are orthogonal in the Hilbert space, which means hn star times hn, each one times this. So here we have minus xi squared in dixi. Then it is a constant times delta and n, which is the Kronecker delta, which means that when m and n are different, this is 0, and when m and n are equal, this is 1. And so this constant here, in particular with the polynomials written in this form, is square root of pi times 2 to the n factorial. Now this is going to be useful to find the normalization constant, because to find the normalization constant we want the product of our functions to be orthonormal in the Hilbert space, which means we want phi n dxc or minus infinity plus infinity, sorry, dx equals delta mn. And to get this, if we write them out with this expression, we have n squared hn e to the minus xi squared in dx equals delta mn. And if we substitute x with lxc, we get L and here dxc. So since we know this expression here, we are going to divide everything by ln squared, and here we will get ln squared, And so here we have that this one is equal to this one, and so this term must be equal to this one. So we have that ln squared is equal to 1 divided by square root of pi 2 to the n factorial. So n squared is equal to this divided by l. You don't see that, sorry. I write it here. So we must have n squared equals to 1 divided by l square root of pi 2 to the n factorial. And so n equals 1 divided by l to the 1/2 pi to the 1/4 square root of 2 to the n factorial. So we have now our normalized expression for phi. Phi n is n times hn to the minus x squared divided by 2 with n equals this. So our functions are polynomials modulated by these decaying exponentials. So if you plot them, there will be something like you take a polynomial with a finite number of roots and it decays at the infinity, or something like this, or like this, and so on. So the form will depend on the value of n, and in particular we see from this expression here that when n is odd, this we will have an h such that h of c equals h or minus c. Sorry, when n is even. So we have a symmetrical polynomial and a symmetrical wave function. Instead, when n is n even, and when n is odd, we will have an anti-symmetrical wave functions. Sorry, I'll write the line here because you can't see below here. And so for even n, we will have something symmetrical like this, or like this. Instead, for odd n, we have something anti-symmetrical, so which passes from the origin and does this, or also this, and so on. Now, for example, we can calculate phi 0. For phi 0, n will be equal to l to the 1/2 pi to the 1/4, and this will be 1, and we will have h0 equal to this 1. Here we have e to the h squared. This is the zero derivative, so the function itself, which is the inverse of this. So h0 is 1, and so phi 0 is going to be this one divided by this. It is l to the 1/2 pi to the 1/4 times e to the minus h squared divided by 2. Then we go to evaluate phi 1, and for phi 1 we will have n equals to this, but this time we have the square root of 2 also, and h1 is going to be minus here e to the c squared, and this is going to be minus c times this one, which is the inverse of this one. So you see, we these two terms always cancel out into polynomial. We will always be left with this term at the infinity there. And so we're saying here we get minus c, which is plus c, and also 2 we will get, sorry, so 2c, This is the Hermite polynomial of degree 1. So our function is going to be 2c times e to the minus c squared divided by 2 divided by to the 1 half by to the 1 4 square root of 2. So we are going to get square root of 2 here. Now we can substitute c equals x divided by L. So here we will get x squared divided by L squared, and same thing here, x squared divided by 2L squared, and here we will have c divided by L, so here we will have L to the 3 halves. So this is phi1, and this is phi0. So it is easy to plot the solutions. For phi0 we will have something like this, and for phi1 which we will have this anti-symmetrical function, which passes from the origin. So this is phi0 and phi1. Now one last consideration about the energy. If you remember, we had made the substitution k squared L squared equals to n plus 1, and k is the rescaled energy, if you remember. So k squared equals to n plus 1 divided by L squared, and this is the rescaled energy h cut squared divided by 2m divided by h cut squared times w, and so the energy W is 2n plus 1 divided by L squared times h cut squared divided by 2m, and if you remember, L squared is h cut divided by m omega, so we substitute here and we get h cut times m omega. So we get for the energy parameter W, h cut divided by 2 times omega times 2n plus 1. And this is indeed the well-known form for the energy parameters, the well-known value for the energy parameters of the quantum harmonic oscillator. It is well known that the harmonic oscillator does not start from zero energy, but from h cut omega divided by 2. And in general, this is a very famous formula, so the Schroedinger equation works pretty well. And this discreteness for the energy is due to the fact that n can take only discrete values, because otherwise we have no physical solutions. So if you take the Schroedinger equation and you make some considerations on the boundary condition in order to have solutions which make sense, you arrive to these results which are in agreement with the experiment, and this is fascinating. So Schroedinger equation is a fantastic equation, and this is a very good example. So it's all for today. See you next time. It has been a pleasure.